Or good evening, depending on which time zone you're joining us from. So our RRI Thursday colloquium speaker today is Irmgard Bischofberger from the Mechanical Engineering Department at MIT. Irmgard works on fluid dynamics. She works on these beautiful patterns that form and grow spontaneously due to instabilities. She works on the drying and non-equilibrium phenomena in soft gels, for instance. As you will find out for yourselves today, very soon, Irmgard is a passionate science communicator. She has a science and arts collaboration with artists and musicians. I'd really ask you to check out her, I really like this, your fascinating 2019 entry in the Gallery of Fluid Motion on blooming patterns in drying drops. Irmgard, thank you so much for agreeing to give the RI colloquium. So Irmgard would like to be interrupted for questions during her talk. Please use her chat box and I shall alert her to a question as and when it arises. And after the talk, of course, please use the raise hand feature. So Irmgard, over to you. Do tell us about the instabilities in lyotropic chromonic liquid crystals.
Thank you so much, Ranjini. And hi, everyone. It's really a pleasure to be here. So thank you so much for the invitation. So let me try to share my screen. All right. So it's a pleasure to tell you today about some of our ongoing work on instabilities and flow-induced structures in lyotropic chromonic liquid crystals. And so this is work that is done primarily by my graduate student, Ching Chang, in collaboration with Ri Chang from the Hong Kong University of Science and Technology and Chuang Zhou from UMass Amherst. And so my lab investigates pattern growth. So we look, for example, at the pattern growth that occurs as a hydrogel confined between two plates is allowed to dry out. We look at the pattern formation that happens as a colloidal suspension drop dries and forms these beautiful fracture patterns. Or we look at the patterns that form as a polymer jet enters a quiescent bath of water. And so what all these seemingly very different systems share in common is that small perturbations to the system can induce growth on very large scales. But the growth is typically due to a competition between different forces acting on the system. So often these patterns evolve in non-equilibrium systems and the growth is nonlinear. And this non-equilibrium nature and nonlinear growth are really two of the reasons why understanding pattern growth still remains quite challenging. And so the story I want to tell you today, or the stories I want to start with, show features of all these characteristics of pattern growth. And the story really starts with patterns from fluid instabilities. And so I thought I simply start by showing you an experiment where we inject at a controlled volumetric flow rate two fluids of different viscosities into the thin gap of a Healy-Shaw cell through a hole in the center of one of the plates. We then look from the top how an outer fluid gets displaced by a second inner fluid. And so this experiment really has the potential to be extremely boring, because intuition tells us that probably the inner fluid is just going to displace the outer one as a stable circular disk. However, whenever a less viscous fluid displaces a more viscous one, luckily the situation is much more interesting. And I'd like to show you a video of what happens in that case. So you're seeing here such a so-called Healy-Shaw system. From the top, the glycerol is already pumped in, and as the movie starts, we inject dyed water through this tubing into the center of the plates. And so you see that as soon as the water invades the glycerol, the interface between the two fluids becomes unstable and fingers grow that grow into fairly complex patterns. So what causes the growth of this so-called viscous-fingering instability? So if we consider a less viscous fluid that displaces a more viscous one, and we consider a spontaneous perturbation that forms at the interface between these two fluids, then the lines of constant pressure, here indicated in black, are distorted right in front of that perturbation. As a result, the pressure gradient is locally larger in front of the perturbation, and so is the velocity. So this leads to an amplification of the perturbation and to the growth of the fingers. And so this viscous fingering instability is characterized by repeated splitting of the advancing fingertips, which leads to these many generations of fingers and these ramified patterns, which belong to the class of dense branching growth. Now, remarkably though, there's a way to actually prevent this ubiquitous tip splitting and instead have stable tips that penetrate into the outer fluid without ever splitting at the tips. And so we can do that by introducing anisotropy in the interfacial dynamics. And so this introduction of anisotropy has really a quite dramatic effect on the pattern growth. If I take the same two fluids under the same conditions, but now in the presence of anisotropy, and I'm going to tell you in a second how we actually do that, we see that the pattern transitions to a very different type of growth, one that is characterized by global symmetries, and that is characterized by stable tips that never tip split. And this pattern belongs to the class of dendritic growth. And so what did I actually do here? How did I introduce anisotropy in the system? So we did it in the simplest possible way by introducing it in the growth environment by engraving a 6-fold symmetric lattice of channels on one of the plates of our system, where these channels then modulate the plate spacing and become the preferred growth direction as the velocity is proportional to the plate spacing squared. So there's two topological control parameters in this system. There's the plate spacing, denoted as B, and the channel height denoted as H. And so indeed, the ratio between H and B then governs the transition from dense branching to dendritic growth. At small h over b, we see dense branching growth. Beyond a certain critical h over b, the system transitions to dendritic growth. Now, everything I showed you so far, so we see this here in data, is consistent with what has been previously reported in the literature quite a while ago. However, all these experiments in the literature and the ones I showed you so far were done at a very particular limit of this viscous fingering instability. The limit where the viscosity ratio between the two fluids is very low. So where I, for example, displace a very viscous fluid with either air or water. What we find is that there's actually a second important control parameter that governs this morphology transition, and that's the viscosity ratio between the two fluids, where we see that increasing the viscosity ratio changes the critical h over b needed to transition to dendritic growth by almost an order of magnitude. So the different symbols you're seeing here denote that this morphology transition is independent of the flow rate and independent of the absolute value of H and the absolute value of B. So it's really just the ratio H over B and now the viscosity ratio that are the two control parameters that govern this morphology transition from dense branching to dendritic growth. Now, the viscosity ratio, though, has an even more dramatic effect in the dendritic regime. So I previously showed you an experiment at very low viscosity ratio, I now want to compare that to an experiment at a higher viscosity ratio at a comparable H/B. So not surprisingly, probably, we saw that at low viscosity ratio, we get a 6-fold symmetric pattern in a 6-fold symmetric underlying lattice. So the dendrites simply reflect the symmetry of the underlying lattice. Now, as we increase the viscosity ratio, though, we see that the pattern transitions towards a 12-fold symmetric pattern, even though the underlying symmetry is still 6-fold. And so this symmetry transition occurs very systematically with the viscosity ratio, where we transition from 6-fold towards 12-fold symmetry by having the growth of an additional generation of dendrites, which we call here the subdendrites, in addition to the 6 main dendrites. We can quantify this symmetry transition by looking at the ratio between the size of the subdendrites over the size of the main dendrites, which goes from a low value indicative of the 6-fold symmetry towards a value of 1, denoting the transition to 12-fold symmetric growth with an increase in the viscosity ratio. Now, both the viscosity ratio and H/B govern this symmetry transition. However, we can rescale all the data by normalizing the viscosity ratio with that with H/B minus some critical H/B star, which gets clear in just a second. Now, what's somewhat remarkable is that this exact same functional form also describes the morphology boundary that I introduced in the beginning. So I can take the same scaling or the same functional form that I used in order to rescale all my symmetry transitions to explain the morphology transition from dense branching to dendritic growth, where here we also see where this H/B star comes from, which corresponds to the critical H/B needed in the limit of very low viscosity ratios. So the picture that here emerges is that we get 6-fold symmetric growth far away from the morphology boundary. Then as we approach the boundary, by either decreasing H/B or increasing the viscosity ratio, the pattern transitions towards a 12-fold symmetric pattern. And eventually, as it reaches a 12-fold symmetric growth, it transitions back to this generic mode of growth of dense branching characterized by tip splitting. So we can observe dendritic growth over a large range of viscosity ratios. And we have identified 2 control parameters, H/B and the new control parameter of the viscosity ratio, that allow us to now controllably tune both the symmetry of the dendrites and the morphology transition between dense branching and dendritic growth. Now, ultimately, though, this symmetry of the lattice still imposes a very strong restriction to the possible patterns that can grow, allowing only for 6 or 12-fold symmetric growth. And indeed, I want to show you a second way how we can introduce anisotropy, which is maybe a bit more elegant, and which is by doing so in the liquid itself rather than in the growth environment. And so we can do that by using liquid crystals, which are intrinsically anisotropic fluids. So we now go back to having 2 smooth surfaces, so no more underlying symmetry. Instead, we use a liquid crystal and displace it with a lower viscosity silicon oil. Now, if we look at this pattern growth on the crust polarizers, the liquid crystal will appear as colorful and the silicon oil will appear as black. And so indeed, in this intrinsically anisotropic system, we can again observe stable tips that never tip split, characteristic of dendritic growth. So before I can tell you more about these patterns, I want to introduce the liquid crystal we are using. We use disodium chromoglycate, which is a so-called lyotropic chromonic liquid crystal. This is a class of liquid crystals which are water-based and which are composed of disc-like molecules that self-assemble into cylindrical aggregates. These cylindrical aggregates then act as the liquid crystalline unit. Now, in this story, we prepare the liquid crystal in the nematic phase, which corresponds to a weight percent of DSCG in water of about 13 to 18%. And so in this nematic phase, all the directors point in a certain direction. So there's a certain degree of orientational ordering, but no translational ordering. So this disodium chromoglycate is a so-called tumbling nematic, which is a different behavior than the liquid crystals you might be familiar with, the thermotropic liquid crystals, the one that we have in our laptop displays. And indeed, typical thermotropic liquid crystals, so those in your laptops, they typically shear align above an Ericsson number of order 1, where the Ericsson number tells us about the competition between the viscous torques acting on the liquid crystal and the Frank elastic torque. So above an Ericsson number of order 1, typically a thermotropic liquid crystal will shear align, taking an equilibrium angle at steady state. However, our liquid crystal is not going to shear align at this critical Ericsson number, but instead exhibits a continuous collective tumbling behavior in the flow. And so keeping this in mind, let's now go back to our pattern experiments where I showed you that we can get dendritic growth as a low viscosity silicon oil displaces the liquid crystal. However, dendritic patterns only appear above a critical tip velocity, which we can tune by controlling the volumetric flow rate of our system. Below that critical value, the system transitions back to the generic mode of growth of dense branching, characterized by repeated tip splitting. Now, this transition from dense branching to dendritic growth happens both for a low viscosity silicon oil, as well as for higher displacing silicon oils, higher viscosity silicon oils. And indeed, the critical tip velocity V star is independent of the viscosity of the displacing fluid. So there's a fixed condition for when we transition from dense branching to dendritic growth in this viscous-fingering instability. So the way we actually quantify these patterns to belong to one or the other growth category is by looking at the temporal evolution of the tip width, measured a certain distance behind the very tip, which remains constant for the stable tips of dendritic growth, but shows these oscillations characteristic of the repeated tip splitting of the dense branching patterns. Now, one striking feature when looking at these images is that the color of the liquid crystal appears very different depending on whether we have a dendritic pattern or a dense branching one. And indeed, this difference in color bears information about the alignment or the director field in the liquid crystal. And so we can characterize this velocity-dependent alignment by measuring the optical retardance in front of a finger along a distance L, both for dense branching and for dendritic growth, where the optical retardance depends on the plate spacing and, more importantly, on the birefringence of the liquid crystal, which depends on the out-of-plane polar angle of the directors. So this out-of-plane polar angle is the angle in between in the direction of the gap. So C is the gap direction, and X here would be the flow direction. And so for the moment, we take this retardance in a somewhat simplified way and interpret it simply as a measure of the average out-of-plane polar angle of the liquid crystal. And so this lower value of retardance that we see in the far field for dense branching growth corresponds to a fairly large out-of-plane angle, which indeed is in agreement with this collective tumbling behavior of the liquid crystal aggregates. However, beyond the critical value, the system eventually gets to a high value of retardance, which means a small out-of-plane angle. And so beyond a certain velocity, the liquid crystal finally shear aligns, adopting an equilibrium angle. And this shear alignment then induces a large enough anisotropy in the viscosity parallel and perpendicular to the alignment direction, which allows for the transition towards dendritic growth. And so we can understand this transition from tumbling to shear alignment by looking at the velocity-induced transitions of the directive field, where we already know that at Ericsson numbers above 1, the material is in this tumbling state. Now, traditionally, we describe the liquid crystal dynamics in terms of the Frank elasticity, or the Leslie-Erickson theory, which takes into account the elastic deformation of the 3 distinct deformation modes of a liquid crystal: splay, bend, and twist. However, such an average description only holds for Deborah numbers much smaller than 1, where the Deborah number denotes the relaxation time times the shear rate. Now, in most of our experiments, though, given that the DSCG aggregates are fairly large, they have a long relaxation time, such that we have Deborah numbers that are larger than 1. And in this regime, we have to think about this in a conceptually different approach, because now molecular elasticity becomes important. And so in this high Deborah number regime, there's 2 competing effects. There's the nematic potential, which tries to keep the aggregates pointing in the same direction and which induces this collective tumbling behavior, and the shear flow, which eventually induces a deformation of the individual aggregates towards the stationary angle, allowing them to shear align. And so we can account for these 2 competing effects by looking at the elastic forces due to the nematic potential, which we here express in terms of an Unsauger type excluded volume potential, and the viscous forces from the shear flow. Now, the ratio between these 2 forces gives us a measure of this competition. To see if this competition indeed governs the transition from dense branching to dendritic growth, we balance the 2 terms, which gives us a critical velocity V star, which depends on 2 parameters that we can control in our experiments: the length of the DSCG aggregates, which we can tune by changing the concentration of DSCG in water, and the plate spacing, which we can tune in the experiment. So I previously showed you an experiment at a fixed concentration, so fixed aggregate length and a fixed gap spacing. Now, changing both the concentration of DSCG in water and the plate spacing change the morphology transition. However, I can rescale all these fairly messy looking data into a clean state diagram by normalizing the velocity with this V star that accounts for that competition between the nematic forces and the viscous forces, which denotes the transition from dense branching to dendritic growth. So there's a critical velocity needed in order to reach a shear alignment, which is set by the competition between the nematic potential and the shear flow. And this shear alignment is necessary in order to induce dendritic growth in the viscous-fingering instability. Now, what this also tells us is that for as long as the material is in this tumbling state, it looks macroscopically isotropic, as evidenced by the dense branching growth in the viscous-fingering instability. And so this is probably a good time to now have a closer look at this tumbling behavior, where we place ourselves in the regime of lower Deborah numbers, where the material is tumbling. And so we use a microfluidic channel with a plate spacing of about 6.5 micrometers. And we again inject at a controlled volumetric flow rate a 13 weight % DSCG solution in water, which again is in the nematic phase. We prepare our surface anchoring conditions, such as the director is planar and aligned in the flow direction, where we define our coordinate system. And this is important, so try to keep this in mind. Our coordinate system is defined such as the flow is in the x direction and the gap spacing is in the z direction. So for these specific surface anchoring conditions at rest, when the material is imaged on the cross polarizers, it appears black. However, as we now start the flow, we see that structures appear. And please note that we are now much more zoomed in than in the previous set of experiments. And eventually these structures reach a steady state size. And so what are these structures that have spontaneously formed on the flow? Why do they have a fairly well-defined size? And why do they appear elongated in the flow? So to answer all of these questions, I need to tell you a bit more about this disodium chromoglycate. So it's a material that is characterized by an exceptionally small twist elastic constant. So a liquid crystal in the nematic phase has 3 modes of elastic deformation. It can either deform in a splay type of deformation, in a twist type of deformation, or in a bend type of deformation. And now for these lyotropic liquid crystals, the twist mode is the energetically cheapest one, where the twist elastic constant is about a factor of 10 smaller than the elastic constants of splay and bend. And so as a consequence of this small twist elastic constant, a director in the shear plane, so in the XC plane, will not want to deform in the shear plane, as this would involve either a splay or a bend type of deformation, but instead it will reorient by a twist deformation towards pointing in the y direction, which is called a log rolling state. So at very low shear rates, the material adopts a so-called log rolling state, where the director orients along the y direction, perpendicular to the flow direction. Only above a certain critical shear rate, the directors reorient back towards the shear plane, where it is then in this tumbling state. And so at these higher shear rates, there's the potential to form topological defects and a variety of structures. And so I'm mentioning here topological defects, so let me tell you what these actually are. And to do so, let me consider my nematic liquid crystal as a school of fish in a pool. And let's imagine that I could hypnotize all the fish at the edges of the pool such that they all swim towards the right. Then the rest of the fish will simply also swim to the right. Now let's imagine, though, that I can hypnotize these fish in a different way, such that those at the edges all swim head to tail. The rest of the fish will then adopt a clockwise rotation. But what about the fish right in the center? It doesn't know where to go. So at the center, we form what is called a topological defect, a region where the director is undefined, or a region where the direction of the orientational order changes discontinuously as I pass through it. And so to probe now if the structures that I showed you in this video are indeed topological defects, we image the system in right field imaging using just one polarizer. In this imaging mode, any topological defect would appear as a dark feature, as the refractive index of the defect core is very different from that of the nematic environment. And indeed, we see many dark features or many topological defects emerge. We can see them nucleate from uniform regions. Sometimes we get lucky and we see them split. And we can see how they annihilate back into a uniform region. And so to learn why these defects form on the flow, we use hydrodynamic Lattice-Boltzmann simulations, which allow us to get access to the director field. And so I'm showing you here a snapshot of the simulation, where we're seeing a side view. So we have here the two plates of a microfluidic channel, and X again is the flow direction. And we see that a really complex director field emerges. We see that the directors are aligned in the flow direction close to the two walls, but they adopt this log rolling state in the center of the plates. And so at the boundaries between these very frustrated regimes, we then see the defects to emerge, which are these red regions here that denote the low order parameter in the system. And so at these frustrated regions, the high elastic stresses of the director gradient get released through the formation of defects. And so this complicated or complex director field is a direct consequence of these shear rate induced transitions, where we have to consider that we have a Poisson-like velocity profile between our two plates, and thus a non-uniform shear rate distribution in the channel, where the shear rate is low in the center, leading to this log rolling state, but then becomes high enough for the material to get back to this tumbling state close to the two walls, exactly what we see in our simulations. Now, the simulations don't only tell us why these defects form, but they also can tell us about the nature of the defects, where we see that they are pure twist disclination loops, these structures indicated here in blue, or again here in this simplified schematics. And we see that these structures, these defects emerge from a local buildup of a twist deformation, which then gets released through the formation of these pure twist disclination loops. So these defects are a direct consequence of the smallness of the twist elastic constant. Now, in order to directly compare our simulations to the experiments, we calculate the retardance map from our director field, which tells us that the low retardance regions appearing as blue are the disclination loops, and the high retardance regions appearing in red correspond to the defect-free regions. Keeping this in mind, we can now go back to our experiments, where we see that the size of these pure twist disclination loops is governed quite strongly by the flow rate of the system. And so to characterize this flow rate dependent size of these pure twist disclination loops, we collaborate with Bao-Liang Gu and Peter Su, who have recently developed a single shot quantitative polarization imaging method that allows us to access in a single image the entire retardance map of our liquid crystal, where again, this is now experimental data, and the low retardance regions correspond to the discontinuation loops. We then calculate a normalized spatial autocovariance in the x direction and the y direction, which gives us access to the characteristic length of these discontinuation loops in the x direction and the y direction. Now, both Lx and Ly decrease monotonically with an increase in the average shear rate. And we define an average length as the square root of Lx over Ly, which decreases with a power law exponent of minus 0.25 with the average shear rate. Now, these discontinuation loops are elongated in the flow, and they have an aspect ratio of about 2. Now, we can show that this length scale is a dynamical balance between the nucleation forces acting on the system, which come from a non-uniform twist deformation throughout the channel thickness, and the annihilation forces from the shear flow. And so I don't want to go into the details of this. All I want to show you is that by balancing the nucleation forces and the annihilation forces, we get a scaling that relates the length scale of these discontinuation loops to the average shear rate with a power law of minus 0.25 in agreement with our experimental data. We can also understand why these loops are elongated in the flow by considering that the characteristic deformation mode across the loop boundary is different in the x direction compared to the y direction. So in the x direction, we predominantly have a bend type deformation across the loop boundary, whereas in the y direction, we predominantly have a splay type deformation. And now evaluating the elastic deformation at the loop boundary gives us a scaling for the aspect ratio that depends on the square root of the bend elastic constant over the splay elastic constant, and predicts an aspect ratio of 1.9, which is in fair agreement with what we see in our experiments. Now, finally, given that we can image the full retardance map in a single image, we can visualize or record this retardance map fast enough to also get information about the dynamics of these pure twist discontinuation loops. And here we have to consider that we actually have two contributions to the dynamics: the somewhat trivial translation in the background flow, but then also the fluctuations of these discontinuation loops, which is what bears some interesting information. And so there's ways to actually decouple these two contributions to the dynamics, such that we can access only the fluctuations and show that the fluctuation time decreases inversely linear with the average shear rate, which we can show essentially reflects directly the tumbling character of this nematic liquid crystal. And so this is quite exciting because accessing this tumbling behavior experimentally is typically quite challenging, but here by looking at the dynamics, we see the direct evidence of this tumbling behavior. So I showed you that we have pure twist discontinuation loops that spontaneously emerge in this pressure-driven flow of DSCG. Their structure is set by the balance between the nucleation forces and the annihilation forces, and their fluctuations reflect the tumbling character of the nematic liquid crystal. Now, I also showed you, or I told you at least, that as we decrease the shear rate even further, we would eventually expect the material to be in this pure log rolling state, which in our visualizations should appear as a uniform yellowish color. However, as we do the experiment, as we try to experimentally push towards lower and lower shear rates, what we see instead is the emergence of stripes. These stripes emerge in these very weak flows. They span over very large length scales. And as we zoom out, we see that they indeed do coexist with uniform regions that are these log rolling states. But what are these stripes? Now, to learn what type of director field is behind this formation of the stripes, we zoom in and do a couple of different visualization tricks. So we can rotate the crust polarizers. And given that we observe that upon this rotation, the dark stripes remain dark, this tells us that at the dark stripes, the directors are homeotropically aligned, which means that they all point in the C direction, so in the gap direction. Now, using a full wave plate retarder allows us to distinguish between these aggregates being aligned in the Y direction or in the X direction. The colors here indicate that they are in between the black stripes, aligned perpendicular to the flow directions, pointing in the Y direction, which suggests that there's a spontaneous twist-like structure that forms on the flow. So such twist-like structures have been seen previously on the different very strong spatial confinements. What our experiments show is that they can also form in the absence of a very strong spatial confinement, but under weak flows. Now, there's a twist deformation along the flow direction. But in order to see the entire director field, we also need to look at what happens in between the two plates. And quite remarkably, we see that in between the two plates, there's also an alternating twist deformation along the gap direction. So let's put everything together, where we see that we have a twist deformation along the flow direction, where I here denote the liquid crystal aggregates simply as a line or as a dot, depending on their orientations. So in addition to the twist deformation in the flow direction, we also have a twist deformation along the gap direction, which now, putting this all together, gives us a periodic double twist structure that spontaneously merges and leads to these stripes with a well-defined period lambda. Now, this period decreases with the average shear rate with a power law of about -0.5. And to understand that, we have to realize that these periodic double twist structures form because of the cheapness of the twist deformation, but they also have a bend type of deformation. And given that the bend deformation mode is more expensive energetically, this is the one that essentially governs the characteristic period of these stripes. So indeed, we can show that the period between these stripes is set by the competition between the viscous torque and the bend elastic torque, so the more expensive type of deformation that we have, which indeed predicts a scaling as 1 over the square root of the shear rate, which is in fair agreement with the experimental data. So to me, these periodic double twist structures are really quite amazing in both kind of their complexity, but at the same time, their elegance that spontaneously shows up here. There's another reason, though, why my student Ching and I are currently so excited about these structures. And that has to do within the broader context of chirality. And so I want to remind you, a chiral object is an object whose mirror image cannot overlap with the original. So our hand is a famous example. So no matter how I translate or rotate my hand, I cannot superimpose the mirror image onto the original. On the other hand, an achiral object can overlap with its mirror image. Now, our twist-like structures belong to the class of chiral objects that cannot overlap, no matter how I rotate them or how I translate them. And so typically, there's two ways of how chiral structures emerge. So I either have a chiral input, which then subsequently generates a chiral output. For example, if I define my boundary conditions such that the liquid crystals are aligned in a certain direction with respect to the plates, and I rotate one of the plates, then I get a chiral output from my chiral input of the plate rotation. Another common way of how chirality emerges, so this is the same as taking a string, turning it around. I have a chiral input, I get a chiral structure. Now, the second way, in the absence of any chiral inputs, of how chiral structures emerge, is if they are made of chiral building blocks. So, for example, nucleotides are chiral, and they create chiral structures of DNA. So chiral building block leads to a chiral structure. Now, what's very rare is a chiral structure that is made of an achiral building block in the absence of a chiral input. And this is what we have in our twist-like structures, which are composed of an achiral DSCG aggregate, which then forms a chiral structure of these double twist periodic stripes. And so this gives you something interesting to think about, because it really asks for what truly are the requirements for a macroscopic symmetry breaking in a material. And so with this, I'm coming to the end of my story. So I hope I could show you some of the rich physics that emerges in these flowing lyotropic liquid crystals. I showed you that as a consequence of the small twist elastic constant that characterizes these materials, they spontaneously form chiral double twist structures or pure twist discontinuation loops. However, macroscopically, all these structures in the tumbling regime look isotropic, as evidenced by the dense branching growth in the viscous-fingering instability. Only above a critical value, where the viscous forces become dominant over the elastic forces, the liquid crystal eventually shear aligns. This then leads to a macroscopically anisotropic material, as evidenced by the emergence of dendritic growth in the viscous-fingering instability. Thank you so much for your attention, and I'd be very happy to take your questions. Thank you.
Madhu, I just wanted to know if you have actually tried to see which sense of the chiral structure each individual twisted structure has.
Yeah, this is an excellent question, and we would love to be able to answer it, but so far we don't know of any experimental technique to do so. So our collaborator, Ri Chang at the Hong Kong Institute of Science and Technology, who does the simulations, is currently working on getting these double twist structures in simulations, but unfortunately we're not quite there yet. But yeah, this is a very important question, and we hope, really hope that we can find either experimentally or numerically ways to investigate that.
And what would happen if you actually chiralize the material? For example, add the DNA or whatever of one sense, so that your liquid crystal intrinsically chiral.
See, that's an interesting thought. So we haven't tried to, for example, mix in small amounts of DNA to see if that would then kind of template the material to go in a certain left or right.
That would normally template, because this is well known in thermotropic liquid crystals.
Yeah, we haven't tried it yet, but it's an interesting suggestion. Yeah, thank you.
That should be very interesting. Anyway, it's a very beautiful set of experiments. Congratulations.
Yes, absolutely. That was
It's
amazing. That was really amazing.
Thank you, Ranji.
Thanks, Imgad. Thank you, Professor Madhusudana. Are there any other questions? Okay, so Sayantan has a question. Sayantan, would you switch on audio and video and ask?
Yeah. Yes.
Nice to see you.
Yeah, same here. Long time. Yes. Great talk. Somehow I cannot. Okay. Okay. I have one question from the first part. You showed that for this six-fold symmetry, you are getting that that finger pattern also it has 6 or 12-fold symmetry. But have you tried it for other underlying symmetries, like for example, say square lattice or something on the substrate?
Yeah, we have tried four-fold symmetry, and you see that exact same transition from four-fold to eight-fold symmetry. Also in that. So this seems to be quite generic, irrespective of the detail of the underlying symmetry.
Okay, and that boundary you defined, it still holds even for other underlying symmetries?
We haven't carefully established the morphology boundary for the fourfold symmetric case. So from the experiments we've seen, we do see the same features in the sense that both H/B and the viscosity ratio matter. We haven't done all the experiments that would actually allow us to get the morphology boundary carefully. Yeah.
Okay.
I think it would remain very similar, but we haven't. We didn't go through the effort of doing it all for the fourfold symmetric case. Yeah.
Okay. So I have another. Maybe you mentioned, but I missed somehow that. Regarding this Deborah number that you mentioned, so if you are keeping the same volumetric flow rate, actually, like as it is getting distributed over larger area, so your shear rate is going down. So I think Deborah number is changing continuously.
Yeah. So in the second part of the So yes, so you're absolutely right. So because we do this all in a radial geometry, our flow rate is changing as a function of the time of the experiment. And that leads to some interesting effects, which means that we can start a pattern in the dendritic growth, and then as it grows and slows down, it transitions to dense branching growth. And so that happens when you are very, very close to the transition, right? Such that within one experiment, because of that effect of a radial slowdown, you transition into the new regime. Yeah.
Because if you are far above the transition point, obviously you need like very large cell to see that.
Exactly. Yeah, exactly. But it is a fun experiment to do, to like place yourself so close that during the time of the experiment you transition back to dense branching growth. Yeah.
Yes. Okay.
But that's exactly what happens. Yeah. So thanks a lot for asking.
Yeah. Thanks.
Okay. I mean, there will be lots of questions, but right now Pallavi asks one in the chat box. So it's all about, from the first part of your talk, should the 6-fold to 12-fold transformation be considered as an eclipse to staggered arrangement?
What does that mean? Maybe
Pallavi, would you just come?
Yeah, that would be awesome. I'd love to learn about that. I haven't heard that transition.
Hello.
Hi. There she is. Yeah. Hi, Pallavi. Hi.
Yeah. Like you showed from 6-fold to 12-fold, or you also mentioned from 4-fold to 8-fold.
Yeah.
So I was wondering whether it should be considered as a one layer having the fingers in one particular orientation, and there is another layer of crystal growth which is shifted a little bit, sheared so from the top, it appears that it is a 12-fold, but actually it is going into a staggered configuration where the 6 fingers from the lower layer are not overlapping with the 6 fingers of the upper layer. Is that something like that?
So basically, I think the question is about the Z direction.
Right. Yeah.
So, which was, I think, the Y
and
direction in your axes.
The gap direction,
Yeah,
right?
yeah.
And it's an interesting question. So all of the experiments I showed today were done with 2 miscible fluids, glycerol and water mixtures. And in these cases, you indeed get interesting structures in the third direction, third dimension, so in between the 2 gaps, the 2 plates, in the sense that your second fluid only fills about half of that plate spacing. We have tried to measure, or we have measured these structures in the third direction, both for the main 6 dendrites and the second generation of these 7th to 12th dendrite. And the 3-dimensional structure of these is very similar. But you are right that the underlying reason for why we get this second generation of dendrites is exactly because of the interaction with the underlying lattice. So it's a question of this penetrating in the fluid. To which extent does it actually feel the underlying symmetry below? And that depends on the viscosity ratio between the 2 fluids. So your question goes in the exactly correct direction. But the structures themselves in the third direction are similar between the subdendrites and the main dendrites.
Okay, thank you.
Thank you.
Thank you. Are there any other questions? Okay, then let me start. Okay, so there is one, Supurna. Oh, Supurna says it's a very nice talk, and we all agree. Palak has a question. So hi, Palak. Would you switch on your video? It's nicer to, it'll be nice to see you. Yeah.
Okay, yeah, sure. Yeah, hi everyone.
Nice to meet you.
Yeah, nice to meet you too. So first of all, very wonderful talk. Love the patterns, like it's a beautiful range of pattern. Since you brought up about the miscibility of the 2 fluids, so I want to know, like, if one tune the interfacial tension between the 2 fluids, so what will happen to these transitions, like this dense branch pattern to dendritic pattern, and will the transition still holds if one tunes the interfacial tension also between the 2 fluids?
Yeah, so it's an excellent question. So, and I only have a partial answer because we haven't done the full set of experiments, but there is some data in the literature in the regime of very, very low viscosity ratios, which shows that the transition between lens branching and dendritic growth still happens also in the presence of surface tension. What surface tension does is it essentially selects the length scale of the fingers.
Yeah.
And so it governs, for example, in the dense branching growth, the moment when these fingers will split, because the surface tension provides an extra cost for that splitting, right?
Yeah, right.
I agree with you that it would be very interesting to essentially look at the higher viscosity ratio regime in the presence of surface tension and to see how that morphology boundary actually changes, or if it changes.
Yes.
We have just done a few kind of test experiments to show that indeed it also happens for the presence of surface tensions of immiscible fluids. But again, we haven't tried to map out exactly the phase boundary.
Yeah, exactly. Because at the higher viscosity ratio, there will be 2 effects, right? Like one stabilization because of the viscosity mismatch, the decrease. And the additional will be the interfacial tension. So, and if we change that, then it would be interesting to see how the transition, whether it will be.
I absolutely agree. Absolutely agree. And we're probably going to try it at some point. It's just we haven't had time to focus on that yet. But yeah, I agree with you that this is interesting to throw.
Yeah, that's all. Thank you. Thank you so much.
Thanks so much, Palak.
Yeah.
So, Irmgard, so would all this, so at least from the first part of your talk, if you increase the thickness of the, the flow gap, at some point it all goes away, right?
Yeah. Yeah.
Okay.
So to be very honest, it has always been a bit of a mystery what exactly, if there is a fixed condition at which it goes away,
Yes,
right?
that
So I
was
don't
my next
think,
question. Yes.
I don't think anyone has very carefully established that, to my knowledge, right? It's just
Okay.
that once you stop being two-dimensional, right, the instability disappears. But I think it disappears in a somewhat fuzzy way and not with a fixed criterion, because increasing the plate spacing, right, in the regular viscous fingering instability, the most unstable wavelength depends on the plate spacing,
Yes.
right? So you
Yes.
get wider and wider and wider fingers.
Right.
And then eventually you just don't get them anymore, right? Then the
Yes.
system is stable once you're not confined enough anymore, right?
Yes.
But I don't know if there is a very clean criterion for when that truly when things aren't two-dimensional enough anymore. Yeah.
Right, right, right. Okay. And I had another question from the liquid crystal part, which is, of course, your liquid crystals are anisotropic, and that's where the anisotropy is coming from. Now, what if you also say nano pattern the surface?
Oh. We haven't tried that. What would be your hypothesis?
I have seen papers where they just, well, I mean, there's no displacement going on, but then they nano pattern the surface of a similar, like a chromonic, a lyotropic liquid crystal, and they see these gorgeous, well, I mean, under the cross polarizers, they see these gorgeous colors that change with the nanopart patterning.
Right. Yeah. Yeah. We haven't started to do that. So we have played with the surface anchoring conditions, right? Which
right,
give
like
you different,
homeotropic and heterogeneous kind of, yeah, okay.
Yeah, yeah. And all of that gets lost as soon as we start the flow, right? So very quickly, everything becomes just flow dominated.
Yes.
I don't know if we could get the longer effects that to some extent wins or at least competes with whatever happens in the flow if we would try to pattern our substrates. It will be a fun experiment to try. Yeah.
Right. I mean, there's just so much that can be done.
I know, too much.
Yes, you never have enough time. I kind of do,
that's a good problem
with that a lot.
have, right?
Yes. Okay. So yes, I mean, this is a lot of fun. I mean, wonderful, beautiful patterns. Are there any other questions? Okay, if there are no other questions, let us thank Irmgard once more for a wonderful talk. And, any other questions, please send them to me. We'll email them over to her. And yes, claps. Please accept our virtual claps.
Thank you so much. And thanks for everyone for all your amazing questions. This was fun for me too. So thank you so much.
There would have been more, I mean, like I said, I mean, we'll keep the questions coming.
Excellent.
Have a nice day.
Thank you so much.
Bye, everybody. Take care.
Bye.